Welcome back. We'll now continue our discussion on, again, we'll go back and look at the turbine calculations. So earlier what we have done is that we have looked at those momentum theory, blade element momentum theory. So now we'll uh, uh, take those things to connect with those calculations, how one can do some sort of design calculations and things like that. So that's the primary motivation here, that we would like to continue with our calculations and some kind of a design procedure. This is very important because you need to see these equations which are there, and that's how you have the uh, now what we'll do, we would try to see what we have done earlier with momentum theory and blade element theory. So we'll actually recall those things, and then from there we'll continue the calculations from there. So what we have earlier done, we have done the linear momentum theory and also the blade element theory. Okay, so this we have done. So analysis here, it is going to, what we are going to do the analysis at this moment. This is going to use these two particular calculations at this moment. Okay, so what we would be doing, essentially, if you look at the momentum theory, that uses kind of a control volume analysis of the forces at the blade based on the conservation of linear and angular momentum. Whether blade element theory, this refers to an analysis of forces at a section of the blade as a function of blade geometry. So now, result of these two, so basically one can say that instead of this, we can say the blade element theory, and of these approaches can be combined, which is known as blade element momentum theory. So combining this is known as blade element momentum theory, BEM theory, which is also we have. So that theory we have also seen, that is used to rotate blade shape of the rotor stability and extract wind. So essentially that uses that wake rotation. So that BEM theory, blade element momentum theory, uses the momentum theory plus blade element theory. Okay, so the simplest optimum blade design with an infinite number of blades and no wake rotation. Then you can have performance characteristics, which is forces, rotor airflow characteristics, power coefficients, and also you can have simple optimum blade design, including wake rotation and a finite number of blades. Now, what we have from the momentum theory, we have is that, so momentum theory gives us the thrust, or the differential thrust, rather differential thrust that you have in terms of dt, which is rho u square 4a 1 minus a pi r dr. So it's essentially, you think about that you have a turbine, and this is the air coming in to the turbine, which is at u, and this kind of a mount and this is your downstate location. So that's your equation number 1. And the torque, which is again the differential torque due to, so the differential torque is essentially due to the tangential force. So that is comes because of B into R into dft. So that here you can have B a prime 1 minus a rho u pi r cube omega dr. So that is what you get. So from this momentum theory, one gets two equation, an equation 1 and 2 that can define the thrust and the torque of an angular sections. Now, if we look at the blade element theory, what we have already got, the forces on the blades of wind turbine, which we can calculate it by expressing there in terms of lift and drag coefficients, angle of attack. So we have already. So there are some assumption. One of the assumption is that there is no aerodynamic interaction between the elements. So there is no radial flow as such, and the forces on the blades are determined solely by the lift and drag characteristics of the airfoil. That we have already done. Obviously, what you need to consider is that the wind, lift, drag, perpendicular forces, parallel forces, effective, relative wind, all these comes into the system, and you can basically can have that omega r plus omega a prime r, which is induced. This is your let's say induced angular velocity, or one can say the tangential velocity, which is omega r into 1 plus a prime. So that is your induced tangential velocity or angular velocity. Now, here we have already, I think earlier we have used the blade pitch angle. So let's say we say blade pitch angle, which is theta p, and if you have blade pitch angle at tip is theta p0, then the blade twist angle is theta t, which is theta p minus theta p0. However, for angle of attack, which is you can write phi, which is p plus alpha. If angle of attack is alpha, so where this is flow angle. So that's, you can say that these are all equation 4 that you have. So essentially these are all the nomenclature that we have already used earlier. Also, you have all the relationship like tan phi, which is 1 minus a by 1 plus a prime lambda r, is 5. Then you have u relative is u into 1 minus a by sine phi, which is 6. Then you have dfl. So we are recalling those expression again. Cl half rho u relative square cdr, and then you have dfd cd half rho u rel square into cdr. Then you have F normal force, which is essentially dfa, axial force dfl cos phi plus dfd sine phi, and you have dft, which is dfl sine phi minus dfd cos phi. So that's what we have already done. So if the rotor blade has b number of blades and total normal force on the section at a distance r, so that we get dfn equals to b into half rho u relative square cl cos phi plus cd sin phi into cdr. Okay, so we are recalling those equations and try to uh, so the obviously our differential torque, which is dq, that would be br into dft. Okay, so our dq becomes b half rho u rel square cl sin phi minus cd cos phi cr dr. Here you can note that the effect of drag is to decrease torque, hence power, but to increase the thrust loading. So blade element theory, one also obtained two equations, which are essentially 11 and 12 or 13, whatever. I mean 11 and 13. So these two equations that you get, so which define the normal force or the thrust force and the tangential force of the torque on the angular rotor section. So these equations would be used. So the relative velocity is effectively that wind which we used earlier, probably W, to determine ideal bed shapes of optimum performance and all this. Now, what we want to now look at is we look at blade shape for ideal rotor. Okay, this case we say that no wake rotation. So we try to, so we can combine the momentum theory relations with the from the blade element theory to relate blade shape to performance. Now, since the algebra can get complex, a simple but useful example can be discussed. So what we can do, we have some assumption for the simple analysis. We'll have some assumption. So no wake rotation, which means A prime is 0. No drag, so that means CD is 0. No losses due to finite number of blades, so that means no tip loss, and then the axial induction factor, which is A equals to 1,3 in each annular steam tube. So you have this. So we have those basic definition of steep speed ratio, number of blades B. So you have all this lambda B R, careful with known lift and drag coefficients. So you can have maximize, I mean CL by CD. Then choose we can choice of twist, chord distributions, and all these things. So what we write for A equals to 1 by 3 from equation 1, we get dt equals to rho u square 4 1 by 3 1 by 1 by 3 pi r dr. So that becomes rho u square 8 by 9 pi r dr, which is okay. Now from equation 11, which is the blade element theory, with CD equals to 0, you get dFn B into half rho u relative square Cl cos phi CdR. Okay. Now another equation is the third equation. The equation 6 can be used to express u relative in terms of known variables. So what from there we can write u relative equals to u into 1 minus a by sine phi, which is 2u by 3 sine phi. So that's now the blade element momentum theory or strip theory refers to the determination of wind turbine blade performance while combining the equations from the momentum theory and blade element theory. Now, using equation 14, 15, and 16, what we get CL BC by 4 pi r equals to tan phi sin phi. Okay. Now we can use equation 5 to relate A prime P based on the geometrical consideration and can be used to solve the blade shape. So equation 5 with A prime 0 and A equals to 1/3, that becomes tan phi equals to 2/3 by lambda r. Okay. So what we have, therefore, we have CLBC 4 pi r 2 by 3 lambda r in sin phi. So now if you rearrange and use lambda r equals to lambda r by r, so one can determine the angle of relative wind. So angle of relative wind and the chord of the blade for each section. So ideal rotor. So angle of relative wind and chord of the blade for each section of the ideal rotor. Okay. So what we get, P equals to tan inverse 2 by 3 lambda r. And from here we get chord equals to 8 pi r sin phi CB CL. So now these relations that you had can be used to find the chord and twist distribution of the optimized blade. I mean, obviously the Bache optimal blade, because we have considered the axial induction factor equals to 1/3. So you can take an example of, let's say, this lambda equals to 7 and carry out this calculation to have all this. Now, what one can see is that the blades designed for optimal power production, so have an increasingly large chord, okay, and twist angle as one gets closer to the blade root. So one consideration in blade design, so blade design is cost and difficulty of blade, difficulty of fabricating the blade. An optimum blade would be very difficult to manufacture at a reasonable cost, but the design provides insight into the blade shape that might be desired for a wind turbine. So this is what you get from the blade element momentum theory, which kinds of combine the which combines the uh, basic momentum theory. And uh, now what we do, we'll move to general rotor blade shape performance prediction. Okay. In general, the rotor is not of the optimum shape because of fabrication difficulties. So when an optimum blade is run at different speed ratio, then one for it is designed, it is no longer optimum. Which is obvious. That's why the blade shape must be designed for easy fabrication and overall performance over the range of wind and uh, range of wind and rotor speed. That so so the so considering non-optimum blades, one generally uses an iterative approach. One can essentially assume a blade shape and predict its performance, then try another blade shape. So these are your iterative process. So for blade shape for an ideal rotor work without wake rotation has been considered. Now what we are going to analysis of here, we are going to analyze arbitrary uh, blade shape. Okay. So that is what we are. Obviously includes this includes wake rotation losses due to finite number of blades, of design performance. So these are the things which we will consider here. So now we would again recall those equations which you have from momentum theory. One is that dt equals to rho u square 4a 1 minus a pi r dr, and dq for a prime 1 minus a rho u pi r cube omega dr. And from blade element theory, we had dfn, which is b half rho u rel square cl cos phi plus cd sin phi cdr, and dq b half rho u rel square CL sin phi minus CD cos phi CR dr. So these are what you have from the momentum theory and blade element theory. So our starting point would be that to move forward with this thing, so that we kind of uses those. So now what we do, using equation 11 and 13 of Behm theory, we write dFn, which is sigma prime pi rho u square 1 minus a square by sine square phi CL cos phi CD sin phi r dr. And we have dq sigma pi rho u square 1 minus a square sine square phi CL sin phi minus CD cos phi r square dr. Where sigma prime is local solidity, which is defined as sigma prime Pc by 2 here. So that is what we have. So what happens is that in general, the calculation of the induction factor A and A prime. So this is the practice to find A prime. We set CD equals to 0. For airfoils with low drag coefficient, this simplification introduces some negligible errors. So when the torque equation from momentum and blade element theory are equated, that is equation 2 and 23 with CD 0. So what we do, using equation 2 and 23 along with CD equals to 0, what we get, A prime by 1 minus A sigma prime CL by 4 lambda r sin phi. So this is 25. So this is what happens is that we are equating torque equation of momentum theory to blade element theory. So these two are equated. Similarly, the normal force equation. So using 1 and 22, so that means you equate the normal force equation of momentum theory and the blade element theory. So what we get, A by 1 minus A sigma prime CL cos phi 4 sine square phi, which is 26. Now you can do some algebraic manipulation using equation 5, which refers to your A prime phi lambda. So what we am saying, that using some algebraic manipulation and using equation 5, 25 and 26, so what you can get, you get CL equals to 4 sine phi cos phi minus lambda r sine phi sigma prime sine phi lambda r cos phi. And what you get, a prime by 1 plus a prime sigma prime cl 4 cos phi. So other useful relationship can be derived. Other useful relationships which are a by a prime equals to lambda n by tan phi, a equals to, so let's say 29, a equals to 1 by 1 plus 4 sine square phi by sigma prime cl cos phi, then a prime equals to 1 by 4 cos phi plus 4 cos phi divided by sigma prime cl minus 1. So this is what you get, that these are the set of equations that you have, uh, that you obtain for this. So now one can look at the solution methods of all these equations that you essentially obtain by doing this calculations, and then we can see. So effectively what one has to do is that finding out this a prime, lambda, c, and all these things. So these are your design parameters, because you have a fixed wind speed, and for that what are these induction factors and CLCT variations and all these things. Okay, we'll discuss about the solution method in the next section.